Welcome to G Fun Facts Online. Today, we're diving deep, thousands of meters below the waves, into a realm of crushing pressure and eternal darkness. For centuries, we saw the abyss as a barren wasteland. But we were wrong. It's a dynamic, chemical factory, a geological forge that has spent eons creating immense fortunes in energy and minerals. So how exactly does the deep sea cook up oil and gas? And how does it grow a treasure chest of valuable metals on the ocean floor? Let's uncover the unseen wealth of the abyss. It all begins with a gentle, continuous snowfall, not of ice, but of life. In the sunlit surface waters, trillions of microscopic organisms like phytoplankton live and die. Their remains sink, creating what scientists call marine snow. Most of it gets eaten on the way down, but a tiny fraction, less than 1%, reaches the seafloor. For this organic rain to become oil, it needs to be protected from decay. This happens in anoxic or oxygen-poor environments. Think of it like vacuum sealing food. Without oxygen, the normal bacteria can't break it down. Instead, specialized anaerobic bacteria begin a slow transformation. Over millions of years, as layers of sediment pile on top, the pressure and temperature rise. This process, called diagenesis, cooks the organic matter into a waxy substance called kerogen. Kerogen is the direct parent of oil and gas. Now, not all kerogen is created equal. Type 1 from algae is a prime oil producer. Type 3 from terrestrial plants washed out to sea mostly makes gas. The most common, type 2 from marine plankton, makes a bit of both. As the rock containing this kerogen gets buried deeper, it enters what geologists call the oil window. Between about 65 and 150 degrees Celsius, the large kerogen molecules crack under the heat, breaking down into the smaller, liquid hydrocarbon molecules we know as oil. If the rock gets buried even deeper, past 150 degrees Celsius, it enters the gas window. Here, the heat is so intense that it cracks the oil itself into even smaller, lighter molecules, primarily methane or natural gas. Once formed, this oil and gas is lighter than the water trapped in the rock around it, so it begins a great escape, migrating upwards. First, it's squeezed out of its source rock in a process called primary migration. Then, it travels through more porous rock layers, like underground highways, in what's called secondary migration. This journey can last for thousands of years and cover dozens of kilometers, until it hits a dead end, an impermeable layer of rock, like a cap or a seal. This is what creates a reservoir. The complex landscape of the deep ocean floor is perfect for creating these traps. Massive underwater avalanches of sediment, called turbidity currents, race across the seafloor, depositing layers of sandstone that make excellent reservoir rocks. These deep submarine fans are where we find many of today's significant offshore oil fields. But there's a fascinating twist. While most oil is fossil fuel, some hydrocarbons might not come from life at all. At hydrothermal vents, where superheated water erupts from the seafloor, a different kind of chemistry occurs. Iron compounds in the rock can react with water to create hydrogen gas. This hydrogen can then react with carbon dioxide from magma to form methane. While this abiogenic oil is likely a tiny fraction of the total, it has huge implications for understanding how carbon cycles through our planet, and even for the possibility of life in similar environments on other worlds. Now, let's shift from energy to a different kind of treasure: raw metals. The deep ocean floor is a vast mineral repository, forged by entirely different, yet equally fascinating processes. First, we have polymetallic nodules. Imagine flying a drone over the abyssal plains, 4,000 to 6,000 meters down. You'd see the muddy bottom littered with trillions of dark, potato-sized lumps. These are the nodules. They are rich in manganese and iron, but they also contain high concentrations of nickel, copper, and cobalt. Metals critical for our modern technology. Their formation is one of the slowest geological processes known, growing just a few millimeters every million years. They form layer by concentric layer, like a tree ring or a gobstopper, precipitating metals directly from the cold seawater onto a central core, which could be a tiny shark's tooth or a shell fragment. This is called hydrogenous growth, but they also grow from beneath. Chemical reactions in the sediment release dissolved metals that precipitate onto the nodule's underside. This is diagenetic growth. It's the activity of deep-sea creatures, constantly stirring the mud, that keeps these nodules from being buried, allowing them to grow for eons. The most famous deposit is the Clarion-Clipperton Zone in the Pacific, an area larger than the contiguous United States. In stark contrast to the slow-growing nodules, we have seafloor massive sulfides, or SMS deposits. These are forged in fire and water at hydrothermal vents, the black smokers. Here, at the boundaries of tectonic plates, cold seawater seeps deep into the ocean crust. It gets heated to over 400 degrees Celsius by underlying magma, becoming a superhot, acidic fluid that leaches metals like copper, zinc, gold, and silver from the volcanic rock. This hot, metal-rich fluid then shoots back up to the seafloor. When this superheated jet hits the near-freezing deep-sea water, the dissolved minerals instantly precipitate, creating a plume of black, smoke-like particles. These particles, actually tiny mineral crystals, settle around the vent, building up huge chimney-like structures and mounds of solid metal sulfide. Interestingly, recent studies show that microbes thriving in these extreme conditions can actually kickstart the process by helping to precipitate the initial sulfide minerals. Our third type of mineral deposit is the cobalt-rich ferromanganese crust. Instead of lying on the mud, these crusts form a slow-growing metallic pavement on the sides and tops of underwater mountains or seamounts. They grow even slower than nodules at just 1 to 6 millimeters per million years, by precipitating metals directly from seawater onto bare rock. Ocean currents are key here. They act like street sweepers, keeping the rock surfaces clean of sediment so the crust can grow, and they constantly deliver a fresh supply of dissolved metals. These crusts are especially rich in cobalt, but also contain platinum and tellurium, elements vital for electronics and green technologies. The richest crusts are found between 800 and 2,500 meters deep, often in what's called an oxygen minimum zone. So we have these vast, untapped reserves of energy and minerals. Naturally, governments and companies are becoming very interested. Exploration relies on incredible technology, remotely operated vehicles, or ROVs, packed with cameras and sonar, mapping the seafloor in stunning detail. The technology to mine these resources is still in development. For nodules, they're designing giant underwater collector vehicles that would essentially vacuum them up and pipe them to a ship on the surface. For massive sulfides and crusts, it would involve massive cutting and grinding machines on the seafloor. But this potential bonanza comes with a huge question mark: the environment. These are not empty landscapes, they are unique habitats. Mining would inevitably destroy these ecosystems, home to slow-growing, often bizarre species that we are only just beginning to discover. Recovery, if it happens at all, could take thousands of years. Beyond the direct destruction, there's the problem of sediment plumes. Mining operations will kick up huge clouds of silt that could drift for miles, smothering nearby habitats that weren't even part of the mining site. The noise and light pollution from 24/7 machinery in a world of perpetual silence and darkness could have devastating effects on marine life. And there's a climate concern. The deep ocean is a massive carbon sink. There are fears that large-scale mining could disturb these deep carbon stores, potentially releasing greenhouse gases back into the atmosphere. Because of these immense risks and the many things we still don't know, many scientists and environmental groups are calling for a moratorium, a global pause on deep-sea mining until we can be sure it can be done without causing irreparable harm to the largest biome on our planet. The deep sea is a world of incredible contrasts. It's where the slow, patient burial of ancient life creates oil, and where the violent, fiery eruption of hydrothermal vents creates mineral chimneys overnight. It's a testament to the complex and powerful geological engine of our planet. As we stand on the brink of potentially exploiting this hidden wealth, we face a profound responsibility. Understanding the geology is the first step, but respecting the fragile and unique life that calls the abyss home is paramount. The unseen wealth of the deep sea presents us with not just a technological challenge, but a moral one. How we choose to proceed will say a lot about our stewardship of the planet. Thanks for listening to G Fun Facts Online.